Welcome to this presentation on linked list. As we saw previously, when we have a pointer to a dynamically allocated array and we need to resize the array to hold more data, the process involves allocating a new dynamic array of a larger size and then copying over the values from the old array or list into the new one, and then deleting or releasing the memory for the old one. This works fine, except when the lists get very large and we're doing a lot of insertions and removals, the amount of time spent copying goes way up. So if you can imagine, if you had a list of 1,000 things and then you need to add more and you need to resize it, then you have to copy 1,000 things and add more. And so for lists whose size changes frequently, this implementation may not be the most efficient, and we're going to start to see a better way in this presentation. Before we get to that, let's take a look at pointers briefly. As you recall, all the data in the memory of our machine, the memory of our computer, has an address. So for example, here we'll declare a variable x that has a value of 7 and a variable y that has a value of 18. So we can represent x as a storage location with 7 and y as a storage location of 18. And what I've shown here in the upper right corner is a number that's supposed to represent their address. Now, as developers, we don't know what those addresses are. When we look at them in the debugger, there'll be some large hexadecimal value, and it will change. If you run it today and run the program tomorrow, those addresses will likely change and not be the same, so we don't really know what they are. So when we declare a pointer to a variable and assign that pointer an address in memory, instead of using the actual number, we usually draw an arrow from the pointer variable to the item that it's pointing to. So that indicates that P is storing the address of X or pointing to X. And so P does not have the value of 7, but it has an address in it that allows it to refer to or point to another variable. If you look at code in the debugger, here we have an array that's set to a few values. And if you look at the array name, you see that it's given as an address, and it happens to be the same as the address of the first element in the array and in the address of the third element in the array. For a 32-bit program, an integer is going to be 4 bytes, so E4 to EC should be 8 bytes away. So if this is 0, then we go 4 bytes and then another 4 bytes to A sub 2, so that would be 8 bytes away. So again, this points out that we don't generally know what the value of an address is. We don't know what the address value is for any particular variable at any particular point in time. We can look at it in the debugger, and it's sometimes useful to know the relative distance or offset from one address, like the beginning of an array, to another. But for most cases, what we want to be able to do is keep track of what pointer variables are pointing to what memory location in a diagram like this. And again, when I code for data structures, I'm always having little pieces of paper around with diagrams that have these arrows and blocks in them. And we talked about the dereference operator, how we can access a storage location with this dereference operation, and here we're assigning a new value, 24, to x, but we're doing it through the pointer p rather than the variable name x. So just showing that as an example. We've seen this where we can create a single dynamic value, or in this case we can create an entire new array dynamically, as shown in the diagrams here. Also keep in mind, when you release or free up the memory, there's two versions of the delete operation. One is delete without the square brackets, which deletes just a single object. The other is delete with the square brackets, that deletes a block of memory if it was allocated with this array allocation syntax. So this is a key step here in understanding how linked lists work. And this isn't unique to linked lists. This step is also used in many other data structures. In C++, a struct is the same thing as a class, except by default all the data members are public. So you can almost use struct and class interchangeably in C++. They just have a different default accessibility. Struct default accessibility is public, and a class's default accessibility is private. We often think of a linked list as a collection of nodes, and so a node is an object that has a data and has some way of accessing another node or another piece of data. So structures cannot be recursive in that we can't declare, in C++ you can't declare a variable of type node inside of a structure. In other languages like C# and Python, you can do that because variables of object type are actually references. They're not actual variables, they're references, which is a similar thing to this pointer operation. So in C++ we use pointers, so we haven't actually declared a node. What we've declared is a variable that's a pointer to a node, and that's perfectly legal. So what this does is it gives us the way to have an object called a node that has a piece of data and also has a pointer to another node. And so this allows us to hook up or link together a series of nodes in a list. We're not going to look at a whole lot of code today, but I do want to point out some of these diagrams and give you an idea of how the basics of linked list work. Typically, we have in a linked list class or a linked list program, you typically have two classes, one for the linked list and one for the node. And in the linked list class, you usually have a pointer to the first node or a pointer to the front of the list. Here we've just have an example code where we've created a pointer to a node and we've set it equal to a dynamically allocated node. And we've set the data value of that node to 8. And notice we use the pointer indirection operator. So it's a hyphen and a greater than symbol that allows us to go dereference the pointer and then access the data part of the node. And we assign an 8 to it. And then here we dereference the pointer, access the next pointer, and we set it equal to a null. And that null value indicates that it's not pointing to anything. So that's a special reserved value. I think it actually has a numeric value of 0. It's a special reserved value that indicates we're not pointing to anything at the moment. And of course, when we're finished with this node, this dynamically allocated memory, we delete it or free it up. So then the next step is to link these nodes together. And I often think of a couple of toys when I think about doing this. One is trains. You know how you have little toy trains and or model trains, and you can link them up. They have little linking bars on each end or one end, and you can link up a train like that. And you can decouple a couple of cars and remove a car from anywhere, from the beginning, from the end, from the middle, and then hook those two end cars that you removed from, hook those back up together. Another one that's kind of fun to think about is this old toy called Barrel of Monkeys, where the monkeys have these curved arms and you can link them together as lists. So either trains or some other object like that where you can link things together is a good analogy, a good way to think about how this works. So again, we've got our class or structure that declares a data and a pointer to the next thing. And here we create a node just like we did before, but instead of setting next equal to null, we set next equal to another node. So now p first next points to another node. And what we've done here is say p first next data. So p first dereference get next, dereference get data, assign 15 to it, and then assign the null to p first, p next, p next. So p first, p next equals null. Now we don't normally access linked list by just chaining on a bunch of p next. This is not the normal way of doing it. We'll see better ways of doing it, but this is just an example, a basic example of how linked lists work. And probably the most important thing is to understand the diagram and the capability of it and how it relates to this analogy of a train of cars, a train of train cars. Notice that in order to add an item to the list, if we wanted to add an item to this list, all we would have to do would be create a new node, have its next pointer point to what is now the first thing in the list, and then have the first thing in the list point to this new node. So let me see if I can draw that real briefly. So if I wanted to make a new node here, then I could draw say a text box. I think I have one. Yeah. So I've just created a new node here, and it has a data part and a p next part. And in order to insert this into the list, so I just allocate a new node with new, and then in order to insert this in the list, what I would do is set the p next part equal to p first. And so that would make this happen. And then I would set p first equal to this new node. I'm not going to show any code right now, but I want you to get the idea of how this works. So if I set p first equal to the new node after I've set the new node's next pointer to be the same thing as p first, then we get this arrow, and then we also get this arrow, and that overwrites this arrow. So the so this arrow is overwritten. This address that points to the node that has 8 in it is overwritten with the address to the new node that was created. So again, to insert a node, the steps are allocate a new block of memory, allocate a new node, set the next pointer of the node equal to the front of the list, which is the same thing as the address that's in p first at the moment, and then set p first equal to the address of this new node, and that makes this arrow now point to this. So now we have a list with one extra node in it. And of course we probably also want to put whatever data value we want to store in there as well. Notice how it's only a handful of steps. It's only about 3 or 4 steps to set up this insertion of a new node in the list. And compare that with having to reallocate and copy thousands of items in the case of the dynamic array, where we may have to allocate thousands instead of just a few, and then copy thousands in order to add an additional item. That's why that linked lists can be substantially more efficient when the list requires many insertions and removals. Because to do an insertion is just a handful of steps, and as we'll see later, to do a removal, again, it's just a handful of steps. You need to access the pointer to the left of it and the pointer to the object to the right of it, and then remove and release this memory, and then hook these back up. And it sounds kind of complex. It's a little bit challenging to understand. These diagrams help a lot, but I think you can see that those handful of steps are going to be less than potentially having to copy thousands of data items from an old list to a new list when the list needs to be resized. One last thing to talk about, and that is what we call list traversal. So when we want to traverse a list or loop through a list, in the case of a linked list, we don't have an array, so we can't use indexing. So I can't say for I equals 0 to the size of the list. Instead, what we do is we create a temporary pointer. Sometimes we call it a walker or a traversal pointer or something like that. And we set it equal to the first thing in the list. So it's going to point to the first item in the list. And then when we're finished printing this out or summing it up or whatever it is we want to do, then we say have this temporary traversal walker pointer, whatever we want to call it, have it update to the next item in the list. So we just say temp equals temp next. So now this particular pointer is going to point to the next item in the list, and we do whatever we want with its value, print it out, sum it up, whatever. When we're done with that one, then we say, okay, this temporary pointer value is equal to temp next, and again we move it to the next item in the list, and again we print it out, sum it up, whatever we're doing with it. And then in this case, when we say temp equals temp next, then this pointer goes away and we get a null value in here. When we reach the end of the list, this temporary traversal pointer will be a null value, and that's the signal to us that we've reached the end of the list. So you'll see something like, you can use a for loop that says temp equals the first thing, the first p first, keep iterating while temp is not equal to null, and then in the update part, temp equals temp p next, so that it moves to the next pointer. So this is a common pattern that you'll see when you need to traverse the list. And sometimes you traverse the list to count up the number of nodes so you can find out what the size of the list is. And sometimes you traverse the list to print them out, or to sum up the values of the list, or to search for a particular value in the list. So we will see more code examples of this in another presentation, but I wanted to show you some of the basics of how a linked list works and how you might be motivated to use a linked list over a dynamic array for efficiency reasons when your data structure, you need a data structure that has many insertions and removals. So let me know if you have any questions about this presentation.